Internal planning operates purely on mathematical probability, but execution requires the physical or digital weight of external systems. A generated plan to book a flight has no inherent way to purchase a ticket. The text string lacks agency. To complete a task, the model must interface with reality. This blueprint illustrates the complete agent loop. It maps how an AI agent repeatedly perceives data, reasons, executes actions, and observes the results until a goal is met. Our deep dive isolates the execution layers on the right, the React control cycle, and tool orchestration. Connecting a language model to these layers creates an active compute node operating within a deterministic software stack. To execute safely, models require a behavioral loop that prevents them from committing to blind, unrecoverable action sequences. The React framework provides this by interleaving reasoning with acting. This diagram conceptualizes React as a continuous three-step cycle: thought, action, and observation. The cycle begins with the thought phase. The model evaluates its current state against the objective and generates internal reasoning about its next move. That reasoning dictates an action. The model executes an external command, like querying a database, or yields a final answer. Every action creates an observation. The system captures the result and appends that feedback directly back into the LLM's context window. This text block demonstrates the literal formatting used in the prompt. The model is instructed to output its reasoning and action payloads using these explicit tags. By forcing the model to pause, execute, and read the resulting observation, the system grounds logic in retrieved facts. This interleaving is the primary mechanism for reducing hallucinations. Actions translate to invoking external tools. These are APIs, search engines, or Python sandboxes that allow the agent to perform precise computation and create side effects. Precision in terminology is required here. Function calling is the model emitting structured arguments. Tool execution is the host system running the code. API orchestration is the higher-level logic managing retries and data flow. Host systems require deterministic syntax. The model's natural language intent must be transformed into a strict JSON object, validated against a schema, and passed to the host API. The model decides which tool to use by reading highly detailed natural language descriptions provided in the system prompt. Clear definitions directly dictate the accuracy of the selection. Rigid schema enforcement guarantees that generated arguments strictly match the expected API parameters, preventing system crashes during execution. Function calling serves as the critical translation layer. It bridges probabilistic reasoning into executable deterministic code. Consider an agent tasked with booking a 2-day business trip from Delhi to Bangalore under a strict budget constraint. This schematic illustrates the core engine TAO loop that will repeatedly govern this process until the booking is complete. The process begins with perception. The agent ingests the budget, travel dates, and corporate guidelines to establish its subgoals. In Cycle 1, the model outputs a thought to search flights, generating the JSON payload. The API executes it, injecting flight times back as an observation. In Cycle 2, it evaluates costs, issuing a new action for a hotel search. After checking corporate policy compliance and total totals, the agent determines the constraints are met and yields the final itinerary. These complex multi-step operations are emergent results of the simple reactive loop adapting to continuous feedback in real time. This stack illustrates where React and tooling sit within the architecture. Top interface and planning layers handle user constraints. Below, the React control loop governs step-by-step decisions. At the foundation, the orchestration layer interacts with APIs and manages errors. System utility is a product of how effectively the outer loop stitches these 4 disparate architectural layers together. Giving an LLM control over an execution loop introduces operational risks. Unconstrained loops represent a severe liability. A poorly prompted agent can enter an infinite loop, repeatedly querying a tool for minor uncertainties while burning through token budgets and increasing latency. Ambiguous tool descriptions lead to schema hallucinations, where the model attempts to use tools that do not exist or proposes unsafe operations, like deleting data. Hard loop constraints are the first line of defense. Developers must enforce maximum step limits and hard-coded execution budgets to forcefully terminate a runaway process. High-impact actions, like financial transfers, must require human-in-the-loop approval gates before the orchestration layer executes the command. Agentic systems are only viable for production if the orchestration layer is explicitly designed to catch deviations and unilaterally halt operations. Maintaining these systems require trajectory logging. Every thought, action, and observation must be persisted to diagnose failures and provide data for future fine-tuning. Evaluating the final output is insufficient. Middle-of-loop failures, like unnecessary tool calls, remain invisible without complete trajectory analysis. This comparison table maps the transition from single-pass prompting to autonomous looping systems with evolving state and explicit tool integration. The role of the developer has shifted toward managing dynamic reasoning engines embedded inside governed, deterministic software ecosystems.